Uh, Hello, everyone. My name is Gupta. I'm an N3S postdoc fellow at UC Berkeley. And I guess the idea of this talk is to give you some expectation of what you can expect to see from ground-based gravitational wave detectors in the next 10 to 15 years, but also maybe touch upon what we have accomplished so far. So since the first observing run back in 2015 all the way till now, the LIGO, Virgo, Kagra detectors have upgraded significantly, each observing run as you go on. And what that has resulted in is that, not just many more mergers of binary neutron stars, well, mostly binary black holes and some neutron stars peppered in between. A lot of them. So here the number 337 is related to the public alerts that the LBK detector sent out. And this is fairly recent. So I think I updated this, a few days ago. And most of these mergers are mergers of black holes. So LIGO, Virgo, Kagra detectors are prolific catchers of binary black hole mergers and even mergers of certain neutron stars. Now, one great snapshot of the advancements that have happened since the first observing run is this event, the loudest event till date, GW250114, which was detected this year in January. And why this is such a nice example is because if you compare it to the first detection, GW150914, the parameters are very similar. The masses are very similar, spins, distance is very similar. But the signal to noise ratio of the first event ever was around 25. The signal to noise ratio of this event, basically the same event in the same detectors but upgraded, is around 80, okay? And so that really drives home the point of how much these gravitational wave detectors have become better in the last 10 years and the kind of precision science that has enabled in the last 10 years or so. And to give you a brief snapshot of what we have accomplished so far, and this is barely even a snapshot because so much has happened, is the first binary neutron star event, GW170817, that was detected back in 2017. This was the first truly multi-messenger event because you saw it in the gravitational wave band, but then you also saw it in multiple electromagnetic bands, okay? And this really enabled you to think about, oh, how can we really constrain the neutron star equation of state, but also about just high energy phenomena, all these electromagnetic transients that are powered by mergers of such neutron stars and what you can learn from them. The other point is that because we see a lot of black holes merging and because our ground-based detectors are fairly good at measuring the mass of those black holes, you can actually create what the spectrum of the masses of black holes looks like. What kind of black holes do we see as they merge? And you can then see that there are very specific features in the spectrum. There's a peak at around 10 solar masses. So these are the kind of black holes that we see more often merging. And then there's a significant drop off beyond 45 solar masses or so when we don't really see black holes in this range. And I guess when you see such things, such features in the spectrum, you can start thinking about astrophysics. What kind of astrophysics would allow you to have such a significant peak at 10 solar masses and then maybe nothing beyond 35 or 40 or so? It allows you to probe how these binaries were formed in the first place. You can also realize that gravitational wave signals, unlike electromagnetic observations, are standard psi events. What that really means is that if you were to detect a gravitational wave signal, you get a direct distance estimate without any external calibrators like electromagnetic observations usually do. And if you get a direct distance estimate, if you have some way of getting the redshift estimate as well, which the cosmology group and the cosmology session will talk about more, then you can actually start constraining cosmological parameters like the Hubble constant. And the hope is that eventually, with more number of observations or maybe more precise observations, we'll be able to constrain the Hubble constant well enough that with gravitational waves themselves, you can start weighing in on this Hubble tension problem. What kind of H0 do you get with a measurement that's completely independent of Planck or Schu's, of supernovae or the cosmic microwave background? And finally, and there are many more things you can do, but finally for this slide, you can also just think about the fact that, well, gravitational waves are predictions of general relativity. So you can then use these gravitational waves to test general relativity itself. And we've done that so far very prolifically. And every time GR has passed with flying colors. So all these things have been accomplished just in the last 10 years. And the natural question that arises is well, what's next? Okay, we are in the fourth observing run. The fourth observing run is supposed to end in the next few weeks, and that's it. After that, the plan is that these detectors go down, they upgrade, and they come back in 2027, 2028 with improved sensitivity, what we know as the A+ sensitivity. And the idea is that you increase the sensitivity by about a factor of 2. So that also increases your range by about a factor of 2 or so, okay? Then the proposal is to improve these LIGO detectors even further with what is called the A-sharp sensitivity, and that's a further improvement by a factor of 2. Okay, so a total improvement by a factor of 4 compared to what we have right now. But already at the A-sharp, you're sort of entering that regime where you're reaching the facility limit of these 4-kilometer long detectors, okay? You can't really tweak technology much more to gain significant gains in terms of science when you are at A-sharp. And so the point is that, well, what do you do then? Do we stop at just 4 times better than what we have right now, or is there something more that you can think about? And that something more is basically building bigger detectors. The American concept for the same is a cosmic explorer network. So that's a 40-kilometer long L-shaped detector and a 20-kilometer detector. So that's an order of magnitude bigger than what we have right now. And you have the European concept of Einstein telescope. So that's a triangular 10-kilometer long detector, or you could have 2 detectors L-shaped that are 15-kilometer long each. Now, as it goes with interferometers, because you have increased the size significantly by almost an order of magnitude, what you gain in sensitivity is also an order of magnitude, simply because you've increased the size. What I'm showing you here are the noise curves. So the lower something is, the more sensitive that detector would be. And you see the gain in sensitivity of an order of magnitude or so, simply because you've increased the size with Cosmic Explorer Einstein telescope. If you also tweak technology, the same technology with which you're upgrading LIGO-like detectors, then you can gain even more at low frequencies and high frequencies, which is where we are not so good right now. But with next generation detectors, the idea is that you'll be able to gain much more there as well. Okay, so why build next generation detectors at all? The idea is very simple. You want more detections. We want to learn more. But you also want better detections. We don't want to stick with observations that have a signal to noise ratio of 20, 25, and we're not able to do very precision science with it. But more than that, we don't just want to keep detecting the same binary black holes every day. You want to detect something different. You want to do more science with what gravitational wave observatories have to offer you. And that is not going to be a problem with these next generation observatories. So what I show you here is 4 possible networks. So one is 3 LIGO-like detectors at A-sharp sensitivity. So something that you may expect in the early 2030s. These 3 detectors, we consider them, 2 of them to be in the US like they are, and 1 of them to be in India as is planned. And then to this network, you start removing 1 LIGO detector and you replace it with 1 next generation observatory. So maybe with a Cosmic Explorer or an Einstein telescope, or you replace it with 2 next generation observatories, or you have a network, the best possible ground-based detector network till date, with 3 next generation observatories, 2 Cosmic Explorers and an Einstein telescope. What I'm showing you here is how many events do you expect to detect with these networks with a signal to noise ratio that's greater than 100. Remember, we've not reached this value yet, so this is already unprecedented. And the numbers are number of detections every day, okay? So the point is that with next generation observatories, you're detecting binary black hole mergers greater than SNRs we have seen so far. And you're not just doing every day, it's basically an hourly thing at that point. And even neutron stars, which we are so which evade us significantly, with next generation observatories, you'll see them once every few days with significant SNR that will allow you to actually probe fundamental physics with them. So more is not going to be an issue. What is also important for us with gravitational wave observations is the fact that we want to be able to localize these mergers well enough in the sky. The idea is, at least for binary neutron star mergers that can then be accompanied with these electromagnetic transients, you want to tell your telescope buddies where to look at, right? And this is more so important for optical telescopes because most of the optical telescopes don't have huge field of views. They have very small field of views. So if you're able to localize events very well in the sky and you can tell people where to look at exactly, they have a higher chance of actually catching the electromagnetic transient that follows a merger. And it so turns out that with next generation observatories, you can actually localize binding neutron star mergers even up to a redshift of 0.4, 0.5, so that's beyond a gigaparsec, to better than 1 square degrees in the sky. Just to remind you, for GW170817, which happened back in 2017, purely from gravitational waves, our localization was order of 10 square degrees, and we could still do a lot. So 1 square degrees or better, it's going to be incredible. But if you could relax it slightly, and maybe you didn't care about localizing things to 1 square degrees, maybe because you didn't care about optical, or because you just had better telescopes, if you allowed your localizations to be as large as 100 square degrees, then you're able to localize these events as far as a redshift of 5, well beyond the star formation peak, okay? And the idea then is that, well, we do see GRBs from that far away. So if you're able to localize events and you get gamma ray bursts there, and if you can actually connect them to binding neutron star mergers, you're then talking about not just seeing neutron star mergers beyond the star formation peak, but also them producing gamma rays, also trying to probe what kind of environments do they lie in. And all of those questions just currently are not reachable for us, okay? I also want to very quickly emphasize the critical role that LIGO India is going to play in all of this. And to do that, I give you a very small example of simulating a binding neutron star merger that's fairly near to us, around 400 megaparsec away, in a 3XG detector, versus if I was to simply remove a 20-kilometer cosmic explorer and replace it with LIGO India at A-sharp sensitivity. And what you see is that your localization on this binding neutron star merger is actually better compared to if you had a 20-kilometer long cosmic explorer in the US, okay? And what this is showing you is that LIGO India, if it comes out in the 2030s, it's going to be extremely important still, because it still does actually better in certain cases than a 20-kilometer cosmic explorer would, even in 2030s, if you're purely concerned about multi-messenger aspects, if you're purely concerned about localizing events and facilitating multi-messenger astronomy. Okay, let's talk about different, because Bruce also touched on nuclear physics, so let's talk about that. So one thing that we can do with gravitational wave observations is that you have neutron stars that are merging with each other, and these neutron stars deform when they're fairly close to merger. And the signatures of these deformations are imprinted in your gravitational wave signal. You can actually use it then to go back and start constraining the equation of state that governs your neutron stars. Okay, what in the gravitational wave context, if simplified, that looks like is basically constraining spaces in the mass versus radius plane of neutron stars. And we did that with GW170817, and it was fairly good. It was still very broad, and it has remained broad because we've only seen 2 binding neutron star events till date. The idea is that even if you don't have any next generation observatories, but you have a bunch of events, you have, let's say, 50 binding neutron star mergers, you can stack them all together. And if you see this black line here, so that's the simulated equation of state, and you see contours around it that sort of constrain that equation of state, that constrain what happens when matter is present in a very dense region, okay? So you can still constrain equation of state without next generation. But the idea is that with next generation detectors, each binary neutron star merger that's close to you, so those are the dots here, each of them gives you a very strong constraint on the radius. You're not stacking all of the events together to get a very strong constraint on your equation of state. Each event gives you a very strong radius constraint, which allows you to constrain the equation of state. But what's different is the following. What if you constrain the equation of state fairly well, and then eventually you got a merger that gives you a constraint like that red dot, or that red dot right there, right? What do you do then? It's very precise, but it's fairly away from the usual hadronic equation of state. Well, if you were to see something like this, maybe that helps you now probe new physics. What if there was a phase transition inside neutron star because the densities were super high? What if neutron stars actually collect dark matter, because of which their internal structure has changed, and that gives you a constraint that looks like this? And that is often possible and made easier when you're able to constrain each event very, very strongly, okay? Talking more about distance, what I show you here are the horizon plots for a 40-kilometer cosmic explorer, basically saying how far can a cosmic explorer detector actually see. And you see that most of the mergers of black holes and neutron stars that we see actually lie fairly within how far a cosmic explorer can see. But the point is that what if the first stars in our universe, the population 3 stars, actually made black holes and those black holes merged at very high redshifts? The idea is that with the next generation observatory, you'll be able to see even those mergers. What if you were to go even further back in the day, right? What if there were primordial black holes that merged at redshifts of 40? Well, the idea is that you'll be able to see even some of those if they were massive enough. So my time is done, so I'll finish. In the ground-based gravitational wave astronomy scene, we've been there for 10 years now, but we're very much just getting started. And with next generation observatories on the line, you're sort of looking at this era of data-rich astronomy, sort of like a paradigm shift that James Webb Telescope had for the Hubble telescope and all the science that it could accomplish. And whenever you have a paradigm shift, whenever you have a data-rich sort of view of astronomy, you also have many other problems. You now maybe have too many signals that you could deal with already, or the signals are too loud. And I know that sounds like a good thing, but what if your models, the systematic errors in your models are now bigger than the statistical errors that you are seeing? And so that's going to be a problem. Another problem is logistical. If there are so many binary neutron stars that you could observe, who observes what exactly? If everyone runs after the best merger, the best neutron star, the best localized, what kind of science do you miss? And is there a good way to actually facilitate that? And all these questions need to be answered now, more or less, because next generation is coming and it's coming fairly soon. Thank you.
Very nice overview, Ish. I had a question about the comparison between CE and LIGO India. You showed one event.
Yeah.
Do you happen to have a sky averaged version of that?
Do you happen to have what, sorry?
A sky average version of
yes,
this comparison?
It's in this paper right here. I can point out, but yes, exactly. We have that. And so if I just briefly summarize it, the point is that for slightly nearby binary neutron star mergers, even from a sky average point of view, LIGO India does better than a 20-kilometer cosmic explorer simply because of the increased baseline. But if you were to look at binary neutron stars at a redshift of 1, let's say, then of course LIGO India just doesn't see it. So it doesn't matter.
You had shown one plot where you were showing the number of events which will have SNR of 100, right?
Yes.
So it looked like on a weekly basis, we may find some neutron star events which would be having an SNR of 100. So do you have any idea for SNR of 1000?
GW170817 has an SNR of 1000 in next generation. That's now a 1 in 50-ish year event. So not very expected.
Okay, so it means that in a year, we may not find many events with SNR of 1000.
With SNR of 1000, yes. You'd have to be fairly lucky. SNR of 1000 has to be within 100 megaparsec or so, which is very close.
Okay, and one more question, that you had shown a plot where you had an outlier in the equation of state. And
yes.
then you were saying that an outlier in the mass radius relation, you can link it either to having a dark matter or a quark sector. But I was wondering that it could be still some other hypothetical objects, right? Like
anything. Yes, I completely agree. People have also talked about strange stars. For that matter, you could have twin stars. You could have a lot. But the point basically is that you could always look at it if your statistical uncertainties do not just cover the entire space. If they're short enough, then you can actually look at it. So, yeah.
Thanks.
Yeah.
Shashwat had a question. Yeah.
Yeah. Could you please go to that mass spectrum plot which you showed right at the beginning?
Right at the beginning, yes.
Yes.
Yeah. Sorry. That's the one bad thing about transitions, right? Yeah, there we go.
Yes. So this excess at 10,
yes.
If I compare that with the kind of masses that we've seen through EM observation of X-ray binaries, we see that, typically their masses are a bit lower. So I'm wondering if it's around that sort of mass, and could that explain why, or do we now have a better understanding of why we mostly see those in EM within the galaxy? They just happen to be more abundant.
I think that's a very good question. And I do agree that I think they're related, definitely. I think one of the slightly more open question about this excess at 10 is the very sharp drop off, right? So if you just have an excess, that's okay. You have an excess right here. The fact that it cuts off very quickly as well requires you to maybe think a bit more about the kind of formation channels that can lead to not just a peak, but also a sharp drop off. But about the X-ray binaries that you see, I definitely think that's related. I don't have a better answer to that.
Yeah, perhaps someone, or maybe someone has already done it, is to do an equivalent mass spectrum with the X-ray binaries and see whether there's some sort of correlation.
That's a good point. Yes, I think that'll be very interesting. Thanks. You had a question?
Yeah, I had a, well, thank you for the talk, by the way, it was very
Thank you.
nice. I have a question about the neutron star equation of state, again, that plot that you had.
Yeah.
So when I first learned about neutron stars and pulsars, I thought neutron stars were kind of like hydrogen atoms or black holes, like they have a mass and a spin.
Yes.
But radio astronomers know that neutron stars have a very wide variety of behaviors, maybe tied to the magnetic field and its structure.
Yes.
So how much does this kind of method depend upon all neutron stars being the same, and how much does it take account of this kind of complexity in structure, mass, and so on?
Yeah, that's a
Very
very good
vague
point.
question, I'm sorry.
No, that's a very good point. And I think to a good extent, at least the method I've shown here, but in general, the methods that are applied do depend on the fact that you consider most of the neutron stars are the same. I know that there are papers that have talked about magnetic field also affecting these neutron stars. I think the idea in general is that by the time they're close to merger, they don't really retain as much angular momentum or magnetic field that it shouldn't matter. But after merger, it's still good. Maybe it's still buried inside and sort of pops up. And the effects from what I have seen are that the magnetic field has to be significantly large for things to actually change significantly.
So the point is that by the time they get close to merger, they really are now simple objects, just a mass and maybe not even a spin anymore.
That is the expectation,
Okay.
yes. But it could always, so I had a work recently, which I didn't put here, which was basically showing that if neutron stars still had some spin, so around tens of milliseconds of period or maybe 100 milliseconds, you could actually measure it eventually with next generation observatories. I guess the idea is that if it were to happen, you'd see it, but there's good astrophysical arguments to this not happening at all.
Yeah, I had a question on the same slide.
Yeah.
I guess a big fraction of these will be at redshifts beyond 1, right? Given the rates we
Yes.
know today.
So I should say that all of these that I'm showing you are within 600 megaparsec. And with current rates, you expect around 20-ish every year, even with current rates. So yeah,
That's well below redshift.
that's well below redshift of 1.
I see. So
Yeah, these are the loudest of the loudest with next
yeah,
generation.
but I think so. Still, the masses will have 10% or tens of percents of.
Not with next
red-
generation. Not with next generation. So that's
No. Redshifted masses.
Oh, redshifted.
So
Well, source wave masses, you mean, because you've also
yeah.
taken,
So the meaning you're assuming that either you know the redshift,
Mhm.
or are you allowing for that correction in these?
I'm allowing for that correction as well. So well, I should say, I say that I know the redshift, or rather I say that I know the cosmology. So I get the distance, I can convert it without an error to a redshift measurement. So my distance measurement is basically by redshift measurement. I'm not taking any uncertainty in edge now. So that is an
Yeah,
assumption
was
that is
my
being,
question.
yes.
Thanks.
Yeah, last question. This is related to what Shashwat asked. If you go to that rate
Yeah.
versus mass.
Yes.
So, I mean, are you sure that in that case there is no selection bias? I mean,
Mhm.
is it clear that this is what the intrinsic is?
So it's taken care for. Yeah. Oh, sorry. So I think the question is that, is this actually intrinsic, or is there a selection effect to the kind of systems that we see? And the selection effect is completely taken care of in any sort of population analysis we do. And so that is why, to a good extent, this is intrinsic, right? Yeah, unless...
Could you say something about the difference like your
Oh, these ones? Yes, I'll very quickly explain because I know we're getting out of time. So when they're fitting to the rates, they want to firstly fit it with something that may be motivated slightly. So they,
This rate is
the bigger of the two masses, the primary mass, also because it's just, measured better. But yeah, so the primary mass. And so initially they fit it with a very sort of a model. So it has to have a broken power law and it has to have 2 peaks. And you then try to say that, oh, what is the index of the first power law, the second power law, and where do peaks happen? But because this is very constraining, it's a model, so they also allow for just a spline fit. And they try to see if there are extra features that appear if you just allow for the flexibility of a spline fit without a lot of model assumptions. And some small extra features do seem to appear, where you'd start seeing that, oh, maybe there's a feature around 20 solar masses.